Hello and welcome to the FM Music Synthesizer February 2021 update. So in this video we're going to talk about the major developments, the less important developments, and the future plans for the project. So to start from the top, the next big thing that I've accomplished with this project is getting the DAC and the microcontroller to communicate over SPI with the FPGA. So within the FPGA module there is a SPI master and SPI slave module. In these, we basically do SPI. I guess basically what I'm trying to say is, if I populate this module down here with byte data to send, and I activate the SPI select line, then it will start sending data out. And the slave works in a similar way, except the SSL active is a signal that comes from an input value rather than something that's controlled in here. So for example, the master select line is something that I control internally, but the select for the slave is something that's controlled externally, so I have it as an input here. In any case, these two modules allow me to communicate both with the DAC and the MCU. The reason that the DAC needs to be needs the FPGA to be a master is because I originally tried doing this by having the microcontroller communicate with both and be the messenger between the two. So the microcontroller would request a sample from the FPGA, and it would get it over SPI, and then it would write that sample to the DAC. But that back and forth was taking too long. So I had to basically just build it into the DAC on its own and have the DAC send data to the DAC chip on its own, basically reducing that latency by about double, or reducing it by half is the better way to say that. And that seemed to work really well. It made the audio signal look way much better. There were little staircases and stuff through it. It's because the microcontroller was taking so long to get the signal from one place to the other. But now it's very fast. It's I think it communicates with the SPI at like 16 megahertz or something fast like that. So in any case, the SPI is working. The next major thing is that I've tested the audio output of the DAC on a speaker, and I've been able to hear it rather well. I'm going to demonstrate what I've heard as best as I can here. I have it plugged into a speaker that might be far away, so if you had a hard time hearing that, please rewind and increase your volume. That should have sounded strange, so I'll go into how that sound is being generated a little bit later when I describe some of the other modules. So the next two big things are the phase modulation, which is doing the frequency modulation, and the unison effect. The frequency modulation portion of this project was going to be the basic method for how this synthesizer was going to be unique. It's one of the fundamental forms of digital synthesis, right up there with additive and subtractive synthesis. Frequency modulation is done whenever the output of one oscillator increases or decreases the frequency of the other, by basically making a one-to-one relationship between, or not necessarily one-to-one, but a direct relationship between the amplitude and the frequency of those two. But in this case, I did some research and found that phase modulation is actually the main way that frequency modulation is achieved. And how that works is, as the amplitude of one sine wave is increasing, if you map that onto the phase of another oscillator, it'll trace through the sine wave as the output of the second one increases, the phase of the first one increases as well. And so it's going to move through the phase of the sine wave faster. And that moving through the phase quickly is actually what appears to make the frequency increase. So you still get the effects of frequency modulation, but you achieve it through modulating the phase instead, which I find unique and interesting and way more easy to implement. So that's what we went for. And here I'll show that. So in here is where the phase modulation happens. We have some inputs from the user, and these are all of these values here. So there's frequency relationships between each of the oscillators, and it's usually done as like some type of multiplier. So the relationship between oscillators 1 and 2 may be a 2 to 1 frequency change, or 1 to 2, or 1 to 3, or 4 to 3, or 2 to 4. Whatever it happens to be, you can configure that here, and that can help you generate more unique effects whenever you actually do phase modulation. And that'll of course come in a later video demonstration, but just saying that now because I felt like it. The next thing is the frequency modulation matrix, and this is what defines the modulation relationships between each of the oscillators. If you want oscillator 2 to modulate oscillator 1, you would increase this parameter. So by default they're all at 0, but they're also signed values. So if you happen to make this, if you happen to increase this value, then you will get that phase modulation in one direction, and then doing it the other way reverses the polarity essentially of the output. So if for instance you wanted to just have it be going the other way, you could do that. But having signed inputs from the beginning is always better when it comes to doing signed arithmetic and Verilog. So that's the main reason why they're signed, but that's just an added bonus. So the next thing about this comes down here with how the modulation matrix actually is implemented. So like I said before, if you want oscillator 2 to modulate oscillator 1, you increase FMM 1-2. And what this does is it just controls the amount that the output of oscillator 2 is increasing the phase modulation of oscillator 1. So this phase M1 goes directly into oscillator 1 right here, and then inside oscillator 1, there's that phase M again. It is added on to the phase that is assigned to the phase to amplitude converter. So there's a phase accumulator. It is not involved with the phase accumulator. It is merely just added on to the output of the phase accumulator, so that we don't mess with that accumulation. We don't advance it by any amount. We just add to the resultant value of the phase accumulator. That way this stays in sync and at the correct it stays in sync with everything else. You know, it's still going to be the same frequency technically, but it's the phase that gets changed. So that is pretty much how the phase modulation works in this. So I've decided to make it work with 4 oscillators, so you can modulate with 4 oscillators in total, and you can actually have feedback modulation, so you can have oscillator 1 modulate its own phase. And I found that the result of this is a sawtooth wave, but of course there's some glitches that happen. In the sawtooth waveform, you go immediately from, I think, like -1 to +1. It's like a ramp, so it basically has that discontinuity, and that discontinuity, whenever it's fed back in, can cause a lot of noise. And just the more that you increase that modulation, the more that noise tends to creep in. So there's an upper limit to this, which is why inside this unit, whenever I am actually, oh sorry, is it over here? Yeah. I say the max feedback is about 87. This value is going to change though, because I just want it to be the full range. I don't want it to merely stop at 87, so I'll work on that. But that's all to say that with feedback modulation, things get a bit more tricky. But both of these were featured in that sound that I played for you, if you could hear it. The modulation was happening like this. So the frequency relationship between all the oscillators is that the first oscillator is at the base frequency, the second one is at 2 times, and then the third one is at 3 times, and then I have a fourth also at 1 times frequency. Then there is no feedback. There is modulation on oscillator 1 from oscillator 2, and then from oscillator 3 to oscillator 1. And then we have the output all the way up on oscillator 1, and then also on oscillator 4, but oscillator 4 doesn't have any modulation. So we're literally just adding the output of 4 onto the output of 1. And I do believe that these are merely added together, or maybe they're averaged. Let me check. Voice mix is a 25-bit, yeah, they're averaged. Yeah, it adds them all up and then truncates the remaining bits on the bottom to bring it back to 16. And that's essentially how I've been, how I average, or how I do division. I try to keep it as a power of 2 and then just do truncations to divide. Ignore this, that is not going to be there in the future. That's another way of dividing if you just right shift everything arithmetically. But I've had so many problems with that in Verilog, it's not worth it. Alright, last big thing is the phase to amplitude converter. So in the beginning, the phase to amplitude converter was a huge lookup table. It essentially was some address that would just increase chronologically, and then based on that address there'd be an amplitude for the sine wave, and it was basically, if you moved through the addresses chronologically, you would trace out a sine wave. So it was very straightforward and kind of lame, but at least it worked, and it worked well for a while. But once I started doing each of these new effects, the phase modulation and the unison effect, I started to use a lot of oscillators simultaneously, like basically at the same time. And the oscillators each used about 6 kilobytes of data for that lookup table. And without muxing, they can't share that lookup table, so I had to just make more and more. And eventually I reached the upper limit and ran out of memory bits available on this specific FPGA. So I decided to go for a more efficient and interesting approach, and I did some research and found an algorithm for a sine wave approximation. This is the point where I bring up MATLAB and go through just how well it compares to an actual sine wave and how it is achieved. I can show you the algorithm here real quick. So we get some value of we basically want some value to increase over time and trace out the sine wave, and so that value is z, and in this case we are going to trace out the first quarter circle of a sine wave. So it'll be that first rising edge, and then once it reaches the maximum, after that point we can use symmetries to, oh goodness, don't need that. We can use symmetries to create the other parts of the sine wave. So right here, ignore the purple line, but you can see, let me make this bigger. You can see we've got 2 lines here. It's actually 3. And this is comparing the original sine wave to a fifth order approximation and a third order approximation. These are polynomial approximations of the first quarter circle, so this part right here. So yeah, I found a very cool online resource that basically showed how you can generate this curve using polynomials that traces out a sine wave. I originally went for the Taylor series approximation, but that wasn't going to work because it was x to the third over 3 factorial and then 5x to the fifth over 5 factorial, and it's like, okay, at that point too much math, not worth implementing. But this polynomial approximation is way simpler, and you can see it gets pretty close enough to be good. If we zoom in, we can see that the fifth order approximation was just so good, like it was right there. So that, and it's not perfect, of course, but it got way closer than the third order, which got pretty close in the first place. So the fifth order I tried first to implement, and it was difficult. There were some values of pi, some coefficients that were decimal values, and at that point I had to essentially I used up a lot of those multiplication units in the FPGA, so it wasn't worth implementing that. Still too much math. So I went for the third order approximation. Decided it was worth the efficiency for the lack of accuracy. And so the actual third order approximation is this equation: z times 3 minus z squared, and that is it. You have to do bit shifting in order to get the everything to operate correctly. Like if you're doing z squared, you need a 32-bit number to fit the 16 times 16-bit number. And then I don't want all the bits in the end, so I truncate again, and then I subtract 3, and then multiply by z, and then do another shift. So it's kind of crazy. That's why you see all these 2 powers in here, like thrown in randomly. And that's to do all that bit shifting. Luckily, MATLAB allows you to do fixed point math and see how well it can do, and then that way when you move to the Verilog version, at least you're not banging your head up against a wall, because it's very hard to figure out. But this works. It's just this small always block where we do z times 3 minus z squared, or negative z times 3 minus z squared, depending on if we're in the first half wave or the second. And then z is assigned this value using a logic. So if we're in the first quarter of the phase, z is going to be just the phase value, and then if it's in the second or fourth quarter circle of the sine wave, it's going to flip z the other way so that it's counting. It's going to do a little bit of transformation. You remember transformation from Algebra 2 or whatever. Oh, Google, are you listening to me? You are. Goodness, ruining my recording. Oh well. So I implemented that, and it seems to save a lot of resources doing it this way. There is error though, and I generated an error graph here to show that happening. Percent error wise, it's like 0.2% error. Actually, here I can just find out. Divide by 2 to the 16, multiply by 100. Okay, it's 2% error. It's a little, there's some error in there, but you know what? At least for the purposes of audio, it really isn't a big deal. And I've listened to both, and I think for what we're doing with it, this approximation is more than enough, especially given the benefits. So anyway, that's the last big thing. The other 2 small things that I did within these 2 months is research the MIDI communication protocol and figure out how to connect that to the system. It's basically UART, so it's basically just serial at some given clock rate, and then it has the same like stop bits and parity things. It's just default. So the one thing I did have to do is fashion a jack in line with a resistor on the supply voltage rail. But that was about it. The rest should just connect to the transmit and receive lines of the microcontroller, and then that'll be connected. I also ordered a new DAC chip, which the PCB has a 3.5 millimeter jack on it, so I can plug the speaker in really easy, compared to the other chip, which is just like some, header pin type deals. I realized that whenever you're looking for a DAC to convert audio signals, you should type in the word audio, because when I typed in audio DAC, this came up, and I think the part is like $10. It's an NXP UDA 1334 chip, and it has a left and right audio channel, and it has a sampling rate that's more than enough because it's meant for audio, so it was designed to work for this. The only issue is it communicates over I2C, and so I would have to fashion an I2C module on the FPGA chip, just like I did for SPI. Fun fact: I didn't write this code. I didn't write this code. I wrote this code for the master. I had to fashion that myself, but it basically works the same as this code, and this was found online. Sometimes it's just easier to research by finding work that other people have already done. And so the way that this works is actually kind of clever. So it synchronizes the SPI and FPGA clocks by like bit shifting in the clock signal, and then that way we can detect the rising or falling edge of the clock. That allows us to basically have the SPI clock signal in here, so that this is, of course, the FPGA is oversampling the SPI clock, so we'll definitely see those edges every time. And then whenever we see the edge, we start bit shifting through the serial line, like you would in of course a serial communication system. So that little tangent out of the way, the future plans are going to be basically this and all the paperwork and documentation that needs to be done. So the first two things that I want to knock out, and I should have ordered this by that so I could talk about them in the right order, but the first thing I really want to do is get this thing developed. So the envelope gain is the main way you control the volume of an audio signal whenever a note is pressed. So if I press a note and it slowly increases to the maximum volume, then that is having a long attack value. After it reaches that maximum and I'm still holding the note and it starts to die off, that is the decay value. The speed at which it dies off is defined by the decay. The sustain value is the value to which that die off happens. So if the sustain is really high, then the decay isn't going to have any effect because it's not going to drop off to a new value. But if the sustain is really low, like 0, then the decay value will basically shut the note off eventually. It'll gradually shut the note off. The release is what happens after the sustain. So a sustain has this dual role of, if it's all the way up, there's no decay, but if the sustain is all the way down, there's no release. So if you have the sustain at some value like 50%, then you're going to press a note, it's going to go to the maximum, it's going to decrease to the sustain value, and then only when you release the note will the rest of the stuff happen with release. And release is the decay after you let go of the note. So release and decay are similar in that way. And that is a crash course in envelope gain using ADSR. So that will be very helpful for when I actually start playing notes on it, it'll help trace that out. So then the next thing, obviously, is to implement the MIDI interface for the keyboard. So I have a piano at home, and I have a MIDI cable, and I have the jack with the resistor in line that I mentioned, and I should just be able to plug that into the microcontroller and then decode the MIDI signals and use that to control the sound generating FPGA hardware. I've done this before with the SPI, so I know the communication works there already. I just need to come up with a protocol of some kind between the two and how to make that work correctly. After those two things, it's pretty much everything else, and then I'll do this at the end. The control interface is basically going to be the main way that the users configure the parameters of the FPGA. It's how they're going to either increase or decrease the phase modulation between oscillators, increase or decrease the frequency relationship. It's how they're going to be able to set the ADSR values of the envelope gain, and then of course change these effects and the unison effect. It is the everything except at the higher level. It's going to have its hands in every part of the system, so of course it's going to take a long time to implement and then a long time to verify that it works. So I really don't know if I should save that for the end or not. Maybe I can get rid of some of these extra effects up here that I want to implement, but if I could get your suggestion there, that would help. So the next things I just want to talk about are these extra effects, and then we'll be done. So the phaser and chorus effect we looked at in RTDSP, so I already know how to do that. In C, I just need to migrate that to Verilog code and put that basically in line with the sample output. And then same thing with reverb and delay. The reverb effect I was researching just one day. I wasn't even thinking about implementing it. And it turns out that reverb is actually very difficult to get working satisfactory. There's a few block diagrams I looked at, and they're very complicated little buggers, so that it might be a little hard to implement, but at the end of the day I'll come out with the most efficient thing that I can that is the most satisfactory. So we'll see how that goes. And then of course the delay effect is probably the easiest one. It literally is a block diagram of basically one delay block summing with the sample output, so that shouldn't be difficult at all. And then the last thing is the LFO, or low frequency oscillator. When in sound design and in synthesizers, it's nice to have a low frequency oscillator which can be used to modulate other parameters of the system without the user having to do anything. So if I want to change the modulation between two oscillators, I can just set it to the LFO, and it'll basically just oscillate that value over time, and it will do it at a low frequency, like maybe 0.2 hertz or something, or 0.1 hertz, something really, really slow. But not terrible. I mean, maybe terribly slow. Actually, it's up to the user at that point. Anyway, that is it. Please let me know what you think. Sorry I dragged this out so long. I tried to record this multiple times, and within that I'm just so glad it's recording, so I'm giving you all the data. I've had a lot of time to run through this and talk about it, so I'm covering more each time. Yeah, but that is it. Thanks.